Welcome, Mr. Shipway here. We're going to look at electron orbitals. So we're saying, alright, we know the electrons are moving around the atom in orbits, is how they've been shown you before, or a probability. They're somewhere around the atom, but we're not sure exactly where or how to determine them. We're going to figure out what shapes they can move in, so we can predict where the electrons are most likely to be found. But to do that, and then write down where they probably are, or where they're most likely to be, we have to then have a way to write that down. So, to look at an example, it's not with electrons. If you're here at Chanhassen and you attend school there, they're the room numbers. They tell you things. So when we write down the room number, it tells you a lot of things. If we look at room number W220, the W tells us what direction or end of the building it's on, the west side. The second digit, the 2, tells us what floor we're on, the second floor. Then the 20 tells you where on that floor the room's located. So in this case, it's farther from the main hall or the main office. Each school, each building will be different, but electrons all use the same type of system. Each number or letter gives you some information about where those electrons can be found. So what we call electrons' room numbers are called quantum numbers. They do the exact same thing. So the way we can think about the electrons' orbitals is to think of them like the rooms in a house or a building. The house has all the electrons in it, but the atoms can only be in certain rooms because they won't all be in the same spot. They're going to spread out. In this quantum model, our room numbers, they're all represented with letters. So different subshells, so different shaped places where the electrons can go, have different orientations or which way they're pointing to go. Like there's a north side, a west side, an east side, a south side. But they're not labeled by north, east, south, and west. But a sphere is a little different, right? You can't tell which side of a sphere you're looking at. If it's symmetrical, it'll look exactly the same from every side. So let's look at a p orbital, which is shaped like a dumbbell or a peanut, in a second. Here's that s orbital. This s orbital can hold 2 electrons. Every orbital we have can hold 2, but sometimes there's more than one in the same energy level. So here there's S stands for sphere. So it's a spherical shape, 2 electrons can be in it. Remember to pause if you need to get this down. Then we have our p orbital shape, or our peanut-shaped orbitals. Now note, there can be 2 electrons in the px, one here, somewhere in there. There's one here in the y orbital. So it's still a peanut shape, but now it's going along the y-axis. Or the z orbital, like it's going back into the board and coming out of the board. That's the z-axis. So the p orbital can hold a total of, or all the p orbitals can hold 6 electrons, 2 in the x, 2 in the y, 2 in the z. Then things get a little complicated when we get to the d orbitals. You can have 5 different d orbitals. And they run along 2 different axes, so like dxy is more complicated, dyz, then you get these really fancy ones. We're not going to make you say what kind of orientations there are, but note that the d orbital stands for like a double dumbbell. There's a dumbbell here and a dumbbell there. Or same thing going this way and that way. 2 of them. So since there are 5 different orientations of the d orbitals, they can hold 5 times 2, or 10 electrons, in the d orbitals. And the last one's a dumbbell with a donut, being the one up here on the left. Then there's the f orbitals. F is a little bit crazy. So we just call F, I'm just going to say it stands for flipping crazy orbitals. We're not going to get into them, they're far too complicated. You can look at them more if you take more chemistry in the future. Alright, so let's actually look at these electron energy levels, or shells. Generally, they're symbolized by N. N stands for the probable distance the electron is from the nucleus, or the energy level it's in. So there's different energy levels that Bohr showed us. Electrons can only be in certain energy levels from the nucleus. So this is the first energy level, going here, second one, third, fourth, fifth, all the way down to the 7th energy level we can have. Now, depending how close they are to the nucleus depends what shapes they can have, or how far away they are. So, different number of electrons can fit in each one. If it's a small circle, small energy level, small area of space, they only fit a certain number of electrons. So, in this case, if Oh, I'll be back. If you're in the n stands for the number of energy levels, right? So if it's 1, you have 2 times 1 squared. Well, 1 squared is just 1 times 2 means we have to have 2 electrons in the first energy level. Then if it was n equals 2 in the second energy level, we now have 2 squared times 2. 2 squared is 4, times 2 is 8. So we have 8 electrons in the second energy level. Going all the way down through 7 you could, but we'll give you a chart here on this next slide that tells you what all of them are. Yes, this looks a little complicated. Don't worry about it too much, I'll explain it to you. So as the energy levels increase, going from 1 to 4, the different types of orbital shapes they can have increases. So there's only S, because there can only be 2 electrons in that first energy level. Then the second we said there's 8 over here on the right, because there can be 2 in the S orbital, and 6 in the 3 different p orbitals. As you go into energy level 3, there'll be 18, because there's S, P, and those 10 that we have in that d orbital, because of the 5d sublevels, or suborbitals. Then we get down to the F1s, which we're not going to focus on too much. There's 32 electrons, and adding that new flipping crazy orbital in there for the bottom one. Those are going a little bit beyond what we're expecting from you guys. But they do exist, they work fine, they're just not very common elements. So, how we represent this on the periodic table and in notation form, what we're going to write down, we use these blocks in the periodic table. So you might want to note where the s orbitals are. So here are your s orbitals, including, look, this little helium could go over here, it should go over there. Then you have your p block. Right, the ones you got px, py, and pz. Something like that. Right, 2 in each, therefore a total of 6. Then we have our d blocks. Make sure you know where these which orbital is in what part of the periodic table. So the F we'll look at a little bit, but not much. They're the ones that get pulled out of the periodic table that really belong right in there between the S and the D's in the bottom 2 levels. Alright, so let me look at a way of how we can explain where the electrons live or what orbital they're in. And come back. Okay, so I like to think of this kind of like you read a book. You always start in the top left, up here. You read the first line, you go all the way across, even though there's a gap there. Then once you finish the first line, you have to go down to the second. In the second line, you're going to read across the second line, and go all the way across, again ignoring that gap, until you finish the line. Then you go to the third one, go across. Then you go to the fourth one, go across. Now there is no gap, because the d orbitals are there as well, because it's big enough, so go straight across. Now, you can think of it like reading a book, but you can also think of it like filling a car. So, let's look at helium. That would be the one right here. It has 2 electrons in its shell, right? The electrons are equal to the number of protons, assuming it's a neutral atom. So the charge is neutral, protons equals electrons, there must be 2 of them there. So, let's say instead of electrons, these are people trying to get in a car. We're going to take a field trip to, let's go to Chicago. Why not? I need to drive down there, but we want to be really energy efficient, so we're going to take the most efficient cars possible, and this little chart tells us where those are. So, I want to say this 1 here. This 1 stands for the first version of a car. It really stands for the first energy level, but for this example, we'll say a car. First version, the S is going to be the s orbital, or the smart car. And smart cars can hold how many people? 2, right? The little itty-bitty smart cars, they don't take much gas, they're very efficient. So we can put 1 person here, second person here, that's a check mark, there we go. You got all the people in there. So we're going to say we have 1s, then we're going to put a little number up above saying how many people are in that car. Or in the first energy level, in the s orbital, there are 2 people. Or in the first version of the smart car, there are 2 people seated in there. Great, so electron configuration is just 1s2. Sweet. But now, what if we had more people coming than just 2 people? Now, let's say we've got another element, like boron. Boron is right here. It's got 5 electrons, because it's the 5th element on the periodic table. So same idea, let's say we're going to Madison this time. We had to bring 5 people in our car. So, like we filled last time, we're going to put 2 people in our first smart car. So that would be 1S2. That's only 2 people, right? There's only 2 people in this car. We need to get 5. So we need to go down to the next row and start here. So we're going to have the second version of our smart car. We're going to put 2 more people in there. Great. Now we've got 2 plus 2, that's 4 people. But we can't bring any more people in these cars. There are only 4 seats. So we have to go across this one to the next one, and now we're going to use the second version of the Prius. They didn't bother building a first version of the Prius. It didn't work at all. In that Prius, to get to this boron one, to get that 5th person, 5th electron, we have to put a 1. It's a bad 1. 1 person in that one. Now we've got 2 plus 2 plus 1 equals 5. The number of electrons we need in it. So the electron configuration would be 1s2, 2s2, 2p1. I'll erase the ink so you can see that better. So boron would be 1s2, 2s2, 2p1. Sweet. Let's try a bigger one. Magnesium has 12. So that's the one down here. Now I'm just going to display this one and talk through what it is. So that's our ending electron configuration. 1s2, putting 2 people in the 1s orbital, or first version of the smart car. Add our 3rd and 4th people into the second version of the smart car, so 1 second version. Then we're going to fill up the Prius. 1, 2, 3, 4, 5, 6. So into the second version of the Prius, it's got 6 people. Gives us a total of 2 plus 2 plus 6 is 10 people. But we need 12. So we're going to go down to the next row, fill the 3rd version of the smart car with 2 people. That gets us our 12, so we're done. That's where we stop our electron configuration. Cool. We got that one. But then what if we get to something like titanium? It has 22 electrons. Okay, well, that's fine. We can keep doing that. So 22. All right, where's titanium? Titanium is right here on the periodic table. Now we're in that D block. So we still have to fill our electrons going 1, 2, which gives us the 1s2. 3, 4 fills our 2s with 2. Then our 2p with 6. 2p, 6. Then our 3s with 2. Not to titanium yet, so we got to keep going. So we do our 3p, and we can fill that one with 6 of them. So 3p6. Then our next one, we gotta go into the 4s. That can hold 2 because it's a smart car. So 4s2. Then 1, 2 into the d's. So a lot of you want to put 4d2. The d2 I agree with, but note, this is a 4s. This is a 3d. The d in my example, my metaphor, we're going to call a dump truck, because after they filled so many cars, like there's 22 kids getting on this trip, you know what? We're just going to put you on a dump truck. We don't even care. And dump trucks take a long time to make, so there's going to be one version behind, and they're really weird how you sit. There's no real seats back there. They just kind of throw you in. They're like, yeah, we can get 10 in there, good enough. So it doesn't quite follow the rules that way, but your D orbitals or your dump trucks are always one version or one energy level lower than your S and P ones. So that'll be your final electron configuration for titanium. Your turn. Try and do it for nitrogen. So go ahead and pause. When you think you have the answer, go ahead and hit play again. It should be 1s2, 2s2, 2p3. If you didn't get that, see if you can figure out why. If not, ask someone. Find your teacher. Say, all right, what did I do wrong? Try number 2. Go ahead and pause. So what is the electron configuration of chlorine? Got to find chlorine first. It'll come out to be 1s2, 2s2, 2p6, 3s2, 3p5. Something a lot of students do wrong is that they say 1s squared, 2s squared, 2p to the 6th. While it looks like that, that's how you'd say it in math. We don't do it that way because we're not squaring the orbital. We're saying there are 2 of them in that orbital. But make sure that the little 2 goes above and not below the s. Lithium, go ahead and pause, do it quick, then hit play. should be 1s2, 2s1. Only 3 electrons total, so there's only be 3. These only add up to 3 for the little numbers on top. Manganese, your state's element if you're living in Minnesota. Hit pause, try it, see if you get the same thing I get. Sweet. Hopefully those are matching up. Hopefully that makes sense. We're going to use it a lot to figure out our valence electrons and charge of atoms in the future. Alright, I want to try one more here. I'm going to back this up for a second and go to an example of a really tricky one. So let's do something like, what would a good one be? We could do something way down there. So we said that this group fits in here, right? So let's do one of them that's in the F group. Let's do, it's a fun one, like cerium. So cerium, element cerium is element number 58. So it's got 58 electrons. You're going to go through this whole thing to get 58 of them. So we're going to go 1s2. It's got 2 electrons. Then we'll go 2s2, 2p6, 3s2, 3p6. That gets us through here. We got to keep going. Then 4s2. It's there, but now remember our D is going to be 1 lower. So now it's 3D. We can fit 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 of them. So 3D10. Then we're back to our 4Ps where we can fit 6 of them. 4P6. Back to our S's, which would go up to 5S2. Back to our D's with our 10 here. Remember, it's always 1 lower, so we're in 5S. Goes to 4D10. Then we go back to our 5P. 5P6, because P always has 6. Now, this group really belongs right there, and this group belongs right here. So after we do our 6s2, we then go to our F orbitals, and cerium happens to be the second one in there, so it'd be F2. But we said D is always 1 lower than S, so then we go to F, and they're actually, no, 2 lower. 6s goes to 4f2. Now, the only analogy that really works with my example would be that this is the freaking fire truck, so we can fit 14 people in there. But this one up here would be your ending electron configuration for cerium. Now, that seems to get awfully long. Now, if we give you a really big one, we might let you do what's called a noble gas shorthand. So, noble gas shorthand, we have to go, all right, if this is our element cerium here, what's the noble gas that comes before it? So we go here, we back it up, go, all right, noble gas would be right here. Nope, sorry, that's the one above. This is our last noble gas. So that noble gas on our periodic tables is radon. So say, all right, we're going to go this, go like this and put radon. That means, those brackets mean we're taking the electron configuration of radon, and then we're going to add to it radon plus these other electrons. So we radon plus 6s2, 4f2. So note, this part is the same as this up above. That is the electron configuration for radon. So it's radon plus that. So note, sometimes we'll make you do the full electron configuration, sometimes it'll be just the noble gas one. But make sure which one we do, because we want the full one, you need the full one. And the thing in brackets, it must always be a noble gas. Can't be any other element.